We assume the ancient buildings still standing today survived because they were built to be completely rigid, solid, and indestructible. But as a structural engineer, I can tell you the real secret is the exact opposite. The ancient structures that last for centuries don't fight natural forces. They are engineered to yield to them. Here is the hidden physics of survival. Welcome back to Next Gen Home Builders. When you look at the Roman Pantheon, ancient Japanese pagodas, or centuries-old European cathedrals, they look like monuments of absolute, immovable force. It's easy to look at those massive stone blocks or heavy timber frames and assume that the key to surviving 1,000 years of earthquakes, soil settlement, and thermal shifts is simply sheer mass. But if you design a modern building based purely on raw, unyielding stiffness, you are engineering its eventual failure. In the physical world, the environment possesses an infinite amount of force. No matter how thick your concrete slab is, or how heavy your load-bearing walls are, gravity, tectonic energy, and moisture will eventually overpower it. The buildings that successfully cheat time aren't the ones that try to stand completely rigid against the planet. The true masterpiece structures survive because their engineers embedded a hidden, counterintuitive secret directly into their skeletons. They designed them to move. How did these ancient builders master structural mechanics before modern computers? The answer begins with a legendary material mystery. To understand this engineering philosophy, we have to look at the forensic chemistry of Roman concrete. For decades, structural engineers have been baffled by Roman harbors and aqueducts that have been constantly battered by seawater for over 2,000 years without degrading. Modern marine concrete often starts deteriorating within a few decades. So what did the Romans do differently? Microscopic analysis of their concrete mixes revealed small, distinct white mineral chunks known as lime clasts. For years, conventional wisdom dismissed these chunks as a sign of poor mixing. But it wasn't a mistake. It was an intentional, high-performance engineering feature. When a Roman structure inevitably experiences minor stress fractures from ground settlement, water infiltrates the crack. As the water passes through, it dissolves the embedded lime clasts, creating a calcium-saturated solution. This solution recrystallizes inside the fracture, physically plugging the gap and sealing the crack from the inside out. The material literally heals itself under environmental stress. Instead of fighting the crack, the structure uses the fracture to trigger its own defense mechanism. But material science is only half the battle. The next secret is entirely mechanical, and it defies everything we see on modern luxury sites. Let's fly across the globe to Japan, where timber pagodas have stood tall through centuries of devastating typhoons and maximum magnitude earthquakes. If you look at a 5-story wooden pagoda, it appears top-heavy and vulnerable. Yet, historically, a fraction of a percent of them have ever collapsed from seismic activity. The secret lies in an astonishing structural device hidden right down the center of the building: the shinbashira. The shinbashira is a massive, independent central log that hangs from the top of the pagoda all the way to the foundation, but it is not rigidly attached to the surrounding floor frames. During an earthquake, the ground shakes the lower floors violently. But because the central column is decoupled from the rest of the framing, it acts as a giant independent pendulum. As the floors sway to the left, the shinbashira sways to the right. The floors slither back and forth like a snake, absorbing and dissipating the kinetic energy through frictional movement instead of trying to resist it with rigid joints. The building literally dances with the earthquake, converting destructive seismic forces into harmless kinetic motion. The structure survives because it is engineered to be flexible. This philosophy of controlled, deliberate movement travels straight into the Gothic cathedrals of Europe. To achieve soaring vertical ceilings and massive window openings, medieval masons ran into a dangerous physical barrier: the outward thrust of heavy stone roofs. If a stone arch wall pushes outward even slightly, the tension will tear the masonry apart, causing a catastrophic structural failure. To solve this without modern steel reinforcement, they engineered the flying buttress, external masonry arms that spring from the upper walls down to massive outer piers. What regular tourists don't realize is that these cathedrals are not monolithic blocks of stone. The mortar used by medieval builders was a soft, flexible lime-based compound, not the rigid Portland cement we use today. This soft mortar allowed the massive stone walls to settle, compress, and flex safely under intense wind loads. The entire cathedral acts like an elastic web of stone, shifting its weight continuously, accommodating the slow, inevitable movement of the underlying soil without snapping. The building behaves more like a living organism than a static object. Now, compare this to the way many modern residential properties are constructed. Today, developers rush to build houses out of high-strength, hyper-rigid concrete mixes, anchored down with unyielding steel connectors, wrapped in airtight membranes. At first glance, this seems like the obvious path to long-term durability, but it isn't the whole story. Because these modern systems are completely unforgiving, they cannot handle unexpected environmental variances. If the ground beneath a hyper-rigid concrete foundation settles by just an inch, the material cannot flex or redistribute the load gracefully. It creates intense internal stress concentration points, resulting in massive structural fractures that compromise the entire framing layout. The ultimate lesson from ancient engineering is that true longevity is achieved when you balance performance with elasticity. The finest historical builders weren't trying to build an indestructible box. They deeply understood soil dynamics, fluid mechanics, and material physics. They designed flexible joints, self-healing material matrices, and independent structural columns because they knew that adaptation is the only true way to defeat time. The secret to building for centuries isn't about matching the raw power of nature. It's about outsmarting it through intelligent, adaptive engineering. When a structure is allowed to move, heal, and breathe, time stops being its enemy and instead becomes the ultimate proof of its design. If you respect the uncompromised physics of building science and love uncovering the hidden mechanics behind great architecture, hit that like button and subscribe to the Next Gen Home Builders channel to help us push this video through the algorithm. Make sure to turn on all notifications so you never miss our deep structural breakdowns. Let me know in the comments, would you trust a house designed to move? Thanks for watching, keep your tolerances tight, and I'll see you in the next analysis.